My name's Kevin, and I'll be your team leader for the evening to start the exam review. So I understand that your exam is on Saturday, and it's going to be over acid-base titrations. So we'll be looking at strong, weak acid, or strong titrations and weak strong titrations, as well as solubility equilibrium and precipitations that can occur from solubility, and how to do like fractional precipitation, like precipitating a certain compound from the solution. And then we'll take a look at free energy and equilibrium on top of that as well. All right, so like the other lectures, we're gonna go through a little review session for the first part, and then in the second half, we'll form breakout rooms to do some of the practice problems that we have created for y'all. All right, so let's go ahead. The formatting is a little weird, but basically there are two types of main titrations that we'll got to keep in mind of. So the first one is strong acid, strong base. So you can either have, so over here to your right, you'll see the layout of what a titration will look like if you've never seen it. So you have an Erlenmeyer flask. Can everyone hear me? Continuing on. Basically, you'll have either an acid or a base in this Erlenmeyer flask, and then you're titrating in the opposite, basically. If you have an acid in here, you'll titrate in a base. Or if you have a base, you'll titrate in an acid. And then we also have a weak acid and strong base titrations. So whatever is your weak is going to be in here. So weak base and strong acid is like the same type of titration, basically. All right. So the weak is in the bottom in that flask, and you're always titrating in a strong. All right. So like I said, there are two types of strong. So there's either acid in the beaker titrating in base, or base in the beaker titrating in the acid. So when you're doing these strong titrations, you have to figure out how many moles of the acid or the base are within the beaker first. And then you need to figure out how many moles of acid or base are added. So then once you figure those out, you want to subtract to see how many moles are left over. And then you want to find the total concentration by dividing it by the new total volume. So I'm going to go back real quick. As you're adding in more liquid, the volume in this beaker changes. And if you guys remember, concentration is basically moles over liters. So as we're changing the liters, we're changing the denominator of that value. And so we have, therefore, a different concentration. All right, so here I have an example kind of written out for y'all. So if we had a beaker of 40 milliliters of 0.150 molarity HCl, and you're titrating it with 25 milliliters of 0.100 molarity NaOH, what's the pH of the resulting solution? So we want to take a look at both the acid and the base. So there, HCl is one of the strong acids, and NaOH, one of the strong bases. So we know it's a strong titration. So let's go ahead and figure out how many moles of acid we have in the beaker first. So we're going to convert the 40 milliliters to liters, and then multiply it by the 0.15 molarity, and you'll get 0.006 moles of the acid. And then same thing for the base. So in case you're wondering how you get moles, moles is equal to liters times molarity. So again, the liters times the molarity, and you get your moles of base. So now we want to subtract them. So it looks like we have less of the base. So we're going to run out of the base first, and then we're going to be left over with moles of acid, HCl. And so the moles of HCl is basically the same as the moles of H+, 1-to-1 ratio. And then from there, let's look at our total volume. So our total volume, right, is 40 milliliters and 25 milliliters, so 65 milliliters. And then we divide by that volume, and we'll get a new concentration H plus, and then we can throw it into our pH equals negative log. You should get 1.27. So also feel free to put in any questions as I'm going through this review. I might not get through to all of them, but I'll definitely get as many as I can. And then we also have other moderators in the chat who will also try to answer your questions. Okay, and here is the titration curve. So this is a graph comparing the volume of your base that you add in. So imagine this is a scenario where you have a beaker that has acid in it, strong acid, and you're titrating in base, strong base. So initially you have just strong acid, so your pH is going to be very low, like it's around 1 right here. And then as you're adding more and more base, it's going to slowly get more and more higher in pH until you hit right here, which is going to be your equivalence point, where your moles of acid and your moles of the base are the same, and you get a sharp jump up. Your pH will be 7, and then as you add more, it's going to be acidic. Solution will be acidic. So there's 3 regions to think about here. One is basically before equivalence point, one is at the equivalence point, and another is after the equivalence point. All right, so we also have weak acid and strong base titrations. So some considerations is the buffer region. So if you have a weak acid and its conjugate base within a solution, you're going to form a buffer. And then at your equilibrium point, your pH will not always be 7. Well, in this case, for a weak acid and strong base, it will not be 7. So earlier I said strong, strong. You will have an equilibrium point where the pH is 7. So there's 4 scenarios, situations. You'll have your initial point. You'll have, are these slides posted anywhere? Yeah, we'll send you a copy of the slides on after the review, and then this video will also be on the YouTube channel for peer tutoring if you'd like to review. Awesome. Okay, so situations, your initial point is before any titrant is added. So you'll just want to do a regular ice table right there, and then before the equivalence point, so you've added in some titrant. So say we have weak acid, strong base, you've added in some strong base. Now you've formed some of the conjugate base of the weak acid. So now you have the HH equation. So at the equivalence point, once you're there, you want to do another ice table. And then after the equivalence point, you're still adding in strong base. Basically, you just have strong base that is reacting, that contributes to the pH. So you want to do negative log of that. All right, so here is a comparison of the 2 titration curves. So if you look at the red, that's what we were just talking about earlier. So strong acid, strong base. You have just like basically a steep slope right here. It's like a little bit of change, and then whoop, big curve, and then plateaus out. Over here, we have the green line, acid, strong base. From here to about to the equivalence point, we have an area called the buffer region. So this one will kind of, what's the word? Kind of mitigate the changes. So there's less of a drastic change as you go up. So compared here, it's a really drastic change. And these are important for processes like in our body. Our blood has a buffer system. All right. Okay, so let's take a look at a problem. I'm just going to go through one long one with you. It's the titration of a weak base with a strong acid. So we're going to go through each of the initial points. Remember I said earlier there's going to be four points. Well, like 5. One of them is kind of the similar enough or the same as another. So at our initial point, right? So we have 50 milliliters of 0.100 molarity of, this is acetic acid. you have the Ka value going to be given to you, and then 0.100 should be molarity NaOH. And so at our initial point, what is that? So we want to set up an ice table, like I said earlier. So we set up ice table, we do our change, and so we'll get these at our equivalence point. And so we set up our Ka value. And here we can do a small x approximation. We can say that this guy is smaller, or the Ka, they're different by a factor over 1,000. So we can do small x. So we have x squared over 0.100. And then just kind of doing the math. You get your x value right there, once you solve for x. That'll be your H plus concentration. So this is why I said that is. And then you plug that number into pH for the negative log, and you get your pH value. So notice it's 2.87. So we'll see it slowly go up as we're getting through this problem. So part B, once you add 10 milliliters of 0.100 molarity NaOH. So what is the reaction that is going on when we have that? Once we start adding. So our reaction here is that we're going to have the weak acid here reacts with the strong base. So we're going to form this salt solution and water. So we can ignore water, right? Water is not important to our calculations. So this salt is going to break apart. If you guys remember, Na plus is a spectator ion, so it's going to break apart from the C2H3O2 minus. So let's go ahead and figure out how many moles of acid we had initially in our beaker. So again, the volume times the molarity gives you the moles of acid. And how many moles of base did we add in? So the volume we were adding in, so 10 milliliters times the molarity, get our moles of our base. So combine or subtract them. So it looks like we run out of our base first. So we'll have 0.004 moles of acid is left. 0.001 moles of this conjugate base should have a minus sign over here, or is created. So remember, we create it over here. And then we know that since we added some base in and we still have acid left over, we're within the buffer region. So we can use the Henderson-Hasselbalch equation. So that's pH equals pKa plus log of the conjugate base over the acid. Okay, so we can get pKa from negative log of the Ka, and then log plus log of the moles of the conjugate base right here over moles of the acid that we have. And then just doing all the math there, you'll get 4.14. So that's a little higher than the 2.87 we had earlier. And we'll see that continue to rise as we add in more acid, or add in more base. All right, so let's see if we add in 25 milliliters of that base. So again, we originally had this many moles of acid, and then where'd you get the 0.001 moles of that? Okay, good question. So notice these guys here, this moles of acid, this is our limiting reagent. So we're combining these two, and this one runs out. Right, so that means we lose 0.001 moles of the acid, which is right here. You're right, basically you subtract it and then you add it to the other side, which is right here. You subtract on this side, you add it to this side. Right, we use HH because we have a weak acid right here and its conjugate base that we formed. So we need both its weak acid and the conjugate base. All right, so back to this one. We had our moles of acid earlier. And so what are our new moles of base that we're adding in? So we'll do volume times molarity, and we get these new moles. And so let's go ahead and combine them again and see. Looks like we run out of base again. So let's see what we have here. So we have 0.0025 moles of the acid is left. 0.0025 moles of conjugate base was created. And notice that they're equal. So that's going to be important. So we're at what's going to be considered the half equivalence point. So where the moles of acid equals the moles of its conjugate base. Conjugate base. So again, we have the acid and we have the conjugate base. So we use the HH equation. So we again do pKa, which I had earlier, which was 4.74 from the previous portion, and then plus log of A minus over HA. Again, they're the same. So we have 4.74 plus log of 1. This is where you guys might not fully get it like right away, because this one has to do with like understanding what the graph of a log looks like. So at log of 1, it's going to be 0. So is what I have here. So it'll just be 4.74. And then a big takeaway from here is that just pH equals pKa at the 1/2 equivalence point. So half equivalence point is, again, where moles of acid equals moles of conjugate base. And then if you know that, you can just kind of ignore this part and then just say pH equals pK. All right, so the next one is adding 50 milliliters of 0.100 molarity NaOH. So what it is, we originally had the 0.005 moles of acid from our other calculations. So how many moles of base do we have this time? So again, volume times molarity, you'll get your moles of base. And so since they're the same value, that means we run out of the acid. So we're at equivalence point. And then we convert all those moles into the conjugate base. And then, yeah, 0 moles of the acid remains. So we need to figure out what the concentration of our conjugate base is. So we know what our moles is, but we need to figure out our volume in order to get that concentration. So we added 50 milliliters, right, to a beaker that already had 50 milliliters. So we have 100 milliliters. So this would be our new concentration. All right, and so setting up an equation, remember, at equivalence point, we want to set up another ice table. So the conjugate base is not just going to do nothing in the beaker. If you remember, the conjugate base of a weak acid is going to want to reform some of that weak acid. And it does that by reacting with the water that's in solution. So it forms the acid again, but by doing so, it produces OH minus as a byproduct. So this is kind of why it's considered a base, because it produces OH minus. And so we plug in our molarity that we got earlier into this ice table, 0, 0, change line, and then we have the equilibrium expressions. So because this is a base, technically this is a base, we cannot use Ka. We'll have to use Kb. And to get Kb, we need to understand the relationship between Ka, Kb, and Kw. So Ka times Kb equals Kw. So that means Kb equals Kw divided by Ka. And Kw is a constant. It's always going to be 1 times 10 to the negative 14 at room temperature, 25 degrees Celsius. And then divided by the Ka we have, so we have our new Kb value right here. Okay, and so we set up the expression that we always set up. Kb equals products over reactants. Again, we can do small x approximation because I say this number and this number are way off by a factor of more than 1,000. And then you just solve for x. So after doing the math, the x comes out to be this value. So that corresponds to our OH minus concentration. And then from there, you just do negative log of that value, you get a POH, and then 14 minus that, you get your pH. So notice, again, that this value is not 7. We're at the equivalence point, I mentioned earlier, but our pH is not 7. It's greater than 7. All right. Okay, so a final scenario. So we're adding in 75 milliliters of 0.100 molarity NaOH. So remember we had 0.005 moles of the acid. So we're finding our moles of the base again. Volume times molarity gives you moles. Let's go ahead and combine those and see what we run out of. We run out of the acid, and we're only left with the base. And only left with the base. So that means we can go ahead and just get the concentration of it right there. So we have our moles over our total volume, which was the 50 milliliters in the beaker, plus 75 that we added in. We have our new concentration, and just do negative log, you get your pH, and then your pOH, and then you get your pH from there. All right. That was basically it for titrations. We'll go next into solubility, product expression, and KSP. All right, so basically, not everything is soluble in water. Some things are partially soluble. So they'll dissolve a little bit, but not entirely. And because this happens, there's an equilibrium that occurs between it. And so this is an example I have right here. Lead iodide is breaking apart in solution. So it's a solid initially. You put it in some water. And so some of them will break out to be lead 2+, and then iodide minus. And then from there, because there's an equilibrium, we can write a KSP value. So K is our equilibrium constant, and SP stands for solubility. So since we're writing out the expression, remember it's products over reactants. So product here, PB 2+ times product over here, I minus squared, because we have a 2 for coefficient here. And we would want to put under the reactant, but our reactants is a solid. And remember, for K expressions, we do not include solids or liquids into our pure solids or pure liquids into our expression. Anything that's aqueous or a gas that we can include. So these guys are aqueous. Here's a little diagram of just like you see something break apart, and it gets stuck in water. Like water surrounds it. It's dissolved. Okay, so there's two types of solubility that the book mentions. There's molar solubility and there's just solubility. So molar solubility is basically the number of moles in one of solute in 1 liter of a saturated solution, versus solubility is the number of grams. So that's where they differ, moles and grams. Still 1 liter of saturated solution. All right, so here's an example problem I have. So it's asking you to estimate the solubility of silver chromate in pure water if the KSP for the compound is 1.1 times 10 to the negative 12. So what I always want to do when I'm looking at solubility of a compound, let's write out the expression. So I have silver 2 chromate, silver chromate basically, breaks apart into 2 silvers and then 1 chromate ion. Then we form an ice table. So we can ignore that because it's a solid, and we know we don't have any in solution yet, so we have 0, and then we go ahead +2 plus 1x. So we have that for our equilibrium portions. So we can set up our KSP value. So KSP here is going to be Ag plus. There's a little 2 right there, so it's squared because we have a 2 in the coefficient right there. And then we have chromate right next to it. All right, and so let's put in all the numbers and all the variables. So here's our KSP equals to 2x squared times x. So we have 4x cubed. So just do the math, divide by 4, take the cube root, and you'll get this value, 6.5 times 10 to the negative 5 molarity of Ag2CrO4. So that's going to be our molar solubility. So what we solved for was the molar. So you'll get molar solubility first, but we were asked to find the solubility. So we want to multiply that by the molar mass, which I have right here, to get the solubility. So this is solubility in terms of gram per liter. This is molar solubility in molarity, which again is moles per liter. Okay, good question. So someone asked, doesn't X represent the CrO4 minus, 2 minus? Yes, so X is going to represent this one as well, but they're also 1-to-1 ratios. So notice that this guy, per molecule of Ag2, CrO4. Okay. Okay, sorry, I think my computer froze for a second. For every molecule of Ag2, CrO4, you have one molecule of CrO4 2 minus. So 1-to-1. So you can say they're the same. All right. So the next part is predicting precipitation reactions. So there can be 3 types of solutions that we have. They are unsaturated, saturated, and then supersaturated. So in terms of calculations, you guys are probably just going to look at probably saturated for the math heavy ones. Okay, and so unsaturated means that you can still add in more solute and it would still continue to dissolve. Like an example was just having a cup of water and then adding sugar to it. So initially you can continue adding a lot of sugar, and then eventually it'll get saturated and you'll have the maximum amount of sugar that will fit inside of a solution. And then we get supersaturated, which means we put in more than what we typically would be able to. So when you're saturated, you won't be able to add in any more solute. Any more that you add in, any more sugar you add in, will fall to the bottom. But we can get a supersaturated solution by heating up the solution. So by changing the temperature, increasing the heat, we can actually cause more than what is typically normal to be added in. Okay, so our Q expression is kind of used to predict when the precipitate might form. So our Q is going to be equal to our cation times the anion. So we always compare Q with K. So if Q is less than or equal to KSP, then no precipitate will form. We're able to continue to add more, or we're at equilibrium, so no precipitate forms, versus Q is greater than KSP, so more precipitate will form. So supersaturated, I saw your questions. Yes, I believe that would be Q is greater than KSP. So it shouldn't have that much, so there shouldn't be that much that is dissolved. And once you cool it down and like you agitate it in some way, like maybe you flick the glass, you'll notice that crystals will grow. Crystals will precipitate out of solution because it's so unstable. Okay, so there are 2 things you guys are concerned about when it comes to affecting solubility. So the first one is the common ion effect. So if you had a compound that is dissolved in a solution that already has another molecule or ion that's in common with it, this is considered a common ion and therefore kind of brings down the solubility of the compound added. So if we want to look at, in this example, so calcium sulfate breaks apart into calcium and then sulfate ions. And so imagine you have a solution, but you already have calcium ions in solution. So there's already calcium. So when you put in calcium sulfate, it's not going to want to move over to the right as much. So it'll move over a little bit more, but not as much. Imagine if you didn't have any of the calcium, it'd want to move over. So therefore, it reduces our solubility because of this kind of equilibrium kind of deal. All right, and so pH is the other topic. So if you have an acidic or basic compound, they will form H plus or OH minus ions in your solution, and this will raise or lower the pH depending on which you have, and this can affect the equilibrium of a compound. So let's look at an example here. We have zinc hydroxide. Then it breaks apart into zinc 2 plus and then plus 2 OH minus. So let's say I add something like I add NaOH to the solution, right? So if we added Na2OH to the solution, now we have too much OH minus. It's going to shift it over back to the left, therefore reducing the solubility. So less of it is dissolved, more of it comes out as a solid. On the opposite hand, if I add in, let's say, a strong acid, say HCl, so HCl comes in, you have H plus floating around. It's going to react with the OH minus, and so it's going to remove this guy from the solution. And so you're missing this guy, and according to Le Chatelier's principle, we're going to shift over to the right in order to compensate to form more OH minus. Therefore, this increases the solubility. All right, so common ion. Okay, so I think I just saw that question. So an example of a molecule with a common ion. So looking at this previous example right here, this would be our molecule that we're adding in. Say we have a solution, but it has something like calcium chloride, CaCl2, and that's already in solution. So we have calcium that's already in solution. So when we add our calcium sulfate in, it's going to lower, it's not going to be able to dissolve as well as it would have without that Ca2+. So we just need an ion that's in common with either the cation or the anion. Will there be a precipitate formed? Yeah, but, well, yeah, potentially, yeah. Really, it kind of depends, but more than likely, however much you're adding in, if you add in like a little bit, maybe no precipitate forms, but if you add in like a bunch, then yeah, some of it will not dissolve. Some of it won't even break apart. It'll just sink to the bottom. It really depends on how much you're adding in. All right, so separation of ions using, yeah, so the pH equation is an example of the common ion effect as well, because you're adding in a common ion, or you can also add in like an opposite ion, like what I was saying with the HCl and the OH minus. If you add in the opposite, it'll actually remove the OH minus. Okay, so separation of ions using differences in solubility. So it's possible to take away one ion from a solution by precipitating it out and leave the other ion in the solution. And this is considered fractional precipitation. So the number with the lowest KSP value comes out first, basically. So you'll typically be given KSP values for compounds. All right, so let's take a look at an example I have. So I have a 1 liter solution with barium 2 plus and strontium 2 plus ions, and you're slowly adding in solid powder of K2CrO4, so potassium chromate. And so the KSP for barium chromate is 1.2 times 10 to the negative 9, and then the KSP for strontium chromate is 3.5 times 10 to the negative 5. So which one precipitates out first? And then how much potassium chromate can you add in without precipitation of any strontium? If the strontium ion solution is 0.0125. Okay, so to know which one precipitates first, you just take a look at your KSP values. So we have KSP for barium chromate to the -9 power, while for strontium chromate is to the -5 power. So we know that the KSP for barium chromate is smaller, so that one precipitates first. All right, so how much of the potassium chromate can you add in without precipitation of any strontium? So we want to look at this KSP value and KSP expression for strontium first. So we have this expression, we set it up here. So let's plug in the numbers. So I said that 0.0125 molarity strontium ions is already in solution. So we place these guys, all the numbers in, so this is where that value would go. And so we end up getting 0.0028 for the concentration of chromate. And so that means we have 0.0028 moles of chromate that can be added in. So let's go ahead and convert that. So it's a 1-to-1 ratio. So with chromate and potassium chromate, so we can say that's the same number of moles. And then I have the molar mass here for you already, 194. And you multiply that, and you get your grams of potassium chromate. So this is the maximum amount, actually, that we can add in. So once you can add it up until this amount, and then strontium. After that, strontium will start precipitating. Strontium chromate will start precipitating out. All right. Okay, so I'll move on to the next part for free energy and entropy.
Hi guys, my name is Grace, and I'm another one of the chemistry peer tutors that's going to be leading the second half of this lecture portion. So as Kevin mentioned, we have this free energy and entropy section, and feel free to put any questions in the chat if they come up. Okay, so first we're going to talk about spontaneity. So a spontaneous process is one that's said to occur under a specific set of conditions. It will occur. And then a non-spontaneous process will not occur under a specific set of conditions. So like in this little picture right here, we have the spontaneous process is the ball going downhill because you don't need to put in any extra energy or anything. It will just roll down on its own. But then a non-spontaneous process would be that ball then try and go back up the hill. It won't just do that on its own. You would have to add some kind of extra force or energy to make that happen. So entropy is defined as a measure of how spread out or dispersed the system's energy is, and this is often correlated with the disorder or randomness of the system. And so you can say that if you increase the disorder, you're increasing the entropy of the system, which would be represented as delta S, because entropy is represented with S. So this can explain how some endothermic processes are still spontaneous, because if you remember from, I think, either the beginning of this class or the end of Gen Chem 1, you talked about delta H being enthalpy, about, exo and endo. So that, I remember them telling you guys that if it's exothermic, that's favorable because it's increasing the heat out in the surroundings. But endothermic was not favorable because you would have to take heat from the surroundings and put it into the system. But by adding this entropy component, this can explain how if you do have an endothermic process, this can still happen spontaneously. So some examples of this would be like dissolving sodium iodide in water, because when you break bonds, you need to add energy for that to happen. So that would be considered endothermic. But if you put that into water or NaCl or any other very soluble salt, you know that if you put salt in water, it will dissociate on its own. That's spontaneous, and that's due to the increase in entropy that we see. Additionally, ice melting above 0 degrees Celsius and water evaporating above 100 degrees Celsius are also examples of endothermic processes that are spontaneous because of the entropy component, helping it to increase the disorder or randomness that kind of outweighs the endothermic that you need to add heat to melt ice or add heat to evaporate water. It still happens spontaneously at those temperatures. And then finally, nature tends to move towards more disordered states, increasing entropy. I remember when I took this class, my professor gave me the example that when you make your room, it's never going to, or sorry, when you clean your room or make your bed or something like that, it's never going to stay like that. It's always going to move towards a more disordered state. Your bed will become undone with your covers and your pillows. Your room will become messy with stuff all over your desk. That's just how the universe tends to gravitate towards. And so that's the same here in chemistry, is that nature and the universe is always gravitating towards a more disordered state, which would be increasing the entropy of the universe. So moving on to a quantitative description of entropy, how can we use numbers with this? So if you'll see this equation up here, the change in entropy of an entire system can be found by doing the change in entropy of at the end of a reaction minus the change in, or that delta S, the change in entropy from the initial, at the beginning of the reaction. And then this is just that in words, basically. The change in entropy for a system is equal to the difference in entropy of the final state and the entropy of the initial state. So in other words, this is a state function, just like enthalpy is. We can use the end and the beginning to figure out the change overall. And then an increase in randomness corresponds to an increase in entropy. So if you look at this little picture down here, you can imagine this is starting out as like a solid. Maybe this is like a block of sugar or something. And then when you put it in water, all of the molecules tend to spread out in increased disorder. This definitely looks more chaotic than this does, right? It's an increase in randomness, which represents an increase in entropy. And then, as I mentioned before, with nature going towards more entropy, an increase in entropy is favorable, and that's what we consider spontaneous if we're looking at entropy alone. So then we have standard entropy, which is the absolute entropy of a substance at 1 atm, which would be standard pressure. Absolute refers to an entropy that would result from the species being taken from absolute zero, so that accounts for the temperature, and brought to a specific temperature. So when you have these standard state values, like you would have in a table, that does not include the temperature. It starts at 0 Kelvin, but you're bringing it to a specific temperature. And so let's say 25 degrees Celsius or maybe 100 degrees Celsius. You have to specify that because the value will be different at different temperatures. It's not part of the standard state definition, and it must be specified. So the units of standard entropy and entropy in general are joules per mole times Kelvin. Note that this is different than enthalpy, which had kilojoules. So when you're doing your calculations, you'll definitely want to make sure that you have them in the same unit. Would concentration be a part of the definition? Concentration isn't so much of a factor here. I mean, you have, I think my computer might have frozen. Can you guys still hear me? Okay, sorry about that. I think my mouse froze, so I thought I froze too. But if you see in the units, we have moles right here. And so that's kind of already accounted for there, but it's not really too much of an issue. You can usually just take the value from the chart. So like I was saying, you want to make sure that your joules and your kilojoules are going to be converted into the same unit. Just choose whichever one is your favorite. But if you don't put the enthalpy and the entropy in the same unit, you won't get the right answer. And then standard entropies in the chart are always positive, even for elements in standard states. And this is different than you'll see with like the delta H of formation, which has a value of 0 for elements in the standard states. So this is something to also note when you're doing your calculations. So here's some trends for standard entropy. These are just ways that you can kind of see qualitatively how entropy of a system would increase if a system did any of these things. So these are kind of like how we talked about within the definition. So it becomes more disordered, more random, more complex, that's all going to increase your entropy. It's kind of like the definition of what entropy is. Additionally, if it becomes more dispersed in terms of energy, so like if we look down here, we start out as a solid and the particles are dispersing themselves as they gain entropy, then all of a sudden you have a gas and they're going all over the place. It's more dispersed in terms of the energy within each molecule, and that is also an increase in entropy. And then we also have if a system is becoming larger, heavier, or hotter. Those will all make the system more disordered and more random, which will increase the entropy. Here are some more standard entropy trends that are definitely good to note when you're looking at qualitatively whether entropy would decrease or increase within a reaction. So number one, the standard entropy of a substance in the gas phase is greater than the standard entropy of that same substance in the liquid or solid phase. And this is because, like this picture from the last slide where we go from solid to liquid to gas, the particles are more dispersed in a gas than they are in a liquid or solid. So this is inherently more random. They're going all over the place. Their energy is spread out, so that's going to cause a greater entropy. Number two is standard entropy increases with molar mass for monatomic species. So if you look at neon gas, it has a greater standard entropy than helium gas, just because neon is heavier than helium. Three, allotropes. This is one that isn't mentioned very often, but I'm pretty sure it was a test question when I took this class, is that more ordered forms, atoms that have less mobility, have a lower standard entropy. So the most classic example of this is that diamond has a lower standard entropy than graphite. If you guys know about diamond and graphite, they're both carbon compounds, but diamond is very much more compressed and solid and harder to break. That's why, getting fancy cuts of diamond is really expensive because it's hard to break it. It's really compressed. And so because of that, it's not going to have as much movement and be as random. And so it's going to have a lower standard entropy than graphite, which, used to be used in pencils. Everybody knows graphite. But allotropes basically just means the same elements and atoms being used to make two different things. So diamond and graphite would be called allotropes, but within the allotropes, diamond has a lower standard entropy than graphite. And then finally, number four, more complex structures have a greater delta S, or not delta, that's just standard entropy, because more types of molecular motion are possible. So an example of that would be ozone, O3, having a greater standard entropy than diatomic fluoride. And this is because if you think about just having, let me see if I can draw, two dots being connected, those really can only move in certain ways. They can go back and forth, up and down. That's pretty much it. But if you have three dots being connected, which represents the ozone, those have a lot more ways they can move because all three of those atoms can move up and down, back and forth, and there's just more types of motion possible. So if you have a more complex structure, that will lead to having a greater entropy. So here are just some more trends about entropy changes that you can use qualitatively to predict how an entropy will change in a reaction. As we talked about, solid is less than liquid, and liquid is less than gas or vapor. Pure solid is less than aqueous, which would be when ions are dissolving in solution. They're becoming more random by being able to move around in the water as opposed to just being in a solid. Then we have low temp is less than high temp, because I mentioned making something hotter will increase its entropy. Fewer moles of gas have a lower standard entropy than more moles of gas, because you have just more going on. There's more different places that they can all exist. And then finally, a smaller volume of gas has less than a larger volume of gas, because if you have more space for them to move around, they can be in a lot of different positions and be more random and more chaotic and stuff like that. So now let's make this distinction between the system and the surroundings, because that's an important note. So the universe can be said as composed of two different components. You have your system, which is the reaction. It's just exactly what you're doing in your reaction at that time. So in this picture, that would be right here in this flask. It says right here, it's the flask and its contents. So right here, that's the system. The surroundings is everything else. So if we were in person and you were going to Gen Chem lab and you were doing reactions every week, you would have your little reaction in your test tube or whatever it is, and then the entire rest of the universe that's not in your test tube is considered the surroundings. So in this example, that's just kind of the rest of the cube, but it says the universe is the system plus surroundings. So altogether, between the two of these, that composes the entire system, or the entire universe. So both the system and the surroundings undergo changes in entropy during physical and chemical processes. So we say that the universe is always gravitating towards a higher entropy. It doesn't always mean that your reaction will be gaining entropy, but the surroundings will be. And so the entire universe is always moving towards a state of disorder and a state of chaos. So that's a little bit existential to think about, but yeah, something will always be increasing in entropy. So now we have the second law of thermodynamics. This says that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. Note that we don't have one that's a non-spontaneous process, because that won't happen and we won't be decreasing entropy in any circumstance. An equilibrium process would just be one that doesn't occur spontaneously in either direction, but you can induce it to occur by the addition or removal of energy from the system when it's at equilibrium. So spontaneous would be the change in entropy of the universe is greater than zero. And remember, we said the universe is composed of the system and the surroundings, and that is increasing. It's going to be greater than zero. Equilibrium, it's going to be equal to zero. So this isn't going to occur on its own, but you can induce it to occur. Basically, it's non-spontaneous, but notice that we are not decreasing entropy of the universe. That just doesn't happen. So entropy changes in system. As I mentioned before, the system is the same thing as the reaction. It's what's happening in your test tube. And so if we're looking at it from a math perspective, when we're going to start adding some numbers into this, you can take this generic chemical reaction and you can calculate the change in entropy of that reaction through this. This probably just looks like a lot of random letters to you, but we're going to walk through this. So C and D are our products, right? The lowercase letters represent the coefficients that would be to your letters, your elements and molecules in this equation. And so we're going to take our C, our coefficient for this molecule, and we're going to multiply it times the standard entropy value of that molecule that you would get from the standard entropy table that will be provided to you. So that's basically what we're doing for all of these. We're taking the coefficient from our balanced reaction and we're multiplying it times the value that you can get from the table. And then if you look, C and D are kind of on the same side, and then we're subtracting A and B from it. And so that's products minus reactants. I know you guys have heard that before. The rule doesn't really change here. You're going to take your products and put them first with their coefficients and their standard state values and subtract the same thing from the reactants. And then stoichiometry does matter, because remember, this whole time these little letters are the coefficients from this reaction. So if they give you a reaction and you don't recognize that it's unbalanced or you forget to balance it, you're not going to get the correct answer, because it's kind of related to, I think someone asked earlier about concentration. This is basically where you account for that. It's about the moles more than the concentration, but you need to have their ratios of values definitely correct so that you can multiply the standard state values times those. And then, as I've been mentioning down here, entropy can be calculated from the table of standard values, just as enthalpy changes were calculated before. So, entropy changes in the surroundings. This is just a little formula that can be useful to help you guys out. So, the change in entropy of the surroundings is directly proportional to the enthalpy of the system. It's negative, but they're both on the top of a fraction. And then the change of entropy is inversely proportional to temperature. So this is a fraction right here. I couldn't get it to look like that, but it's negative delta H of the system over temperature. So that is inversely related to the delta S of the surroundings. Now the third law of thermodynamics is that the entropy of a perfect crystalline substance at 0 Kelvin is 0. So this law allows us to calculate the absolute entropies, which we talked about earlier, for substances by using the value at absolute 0 as a reference point. So if this wasn't 0, it would be a lot more difficult for us to figure out the absolute entropies because we would have no idea where it started from. But because this third law of thermodynamics exists, we can have this table of values that we can create because of this. And so this is different than the enthalpies for substances, which I also mentioned briefly earlier, which we can only write the delta H of formation, but that's not necessary for this because we can say that the entropy of a perfect crystalline substance at 0 Kelvin is 0. So Gibbs free energy. I know you guys were waiting for this to come up. You're like, where's delta G? So Gibbs free energy uses entropy, S, enthalpy, H, and temperature, T, to determine whether a process is spontaneous. So we can't use delta H alone. We can't just say if it's exothermic, if it's releasing heat, that's spontaneous, because we already talked about how that didn't happen. We talked about all those endothermic processes that are actually spontaneous because of delta S. But at the same time, we can't just say that if our delta S, if our randomness, our disorder is increasing, that it's going to be spontaneous, because that's not always the case either. We need Gibbs free energy to relate those with the temperature to determine whether the process overall is spontaneous. And so another thing I mentioned earlier, take a look at these units. Our delta G is in kilojoules, our delta H is in kilojoules, but our delta S is in joules. So I find it easier to just change the delta S into kilojoules when I'm doing these problems because it's just one calculation as opposed to turning these both into joules, but whichever you prefer, you just need to make sure that all of the units are the same. And additionally, this temperature right here is in Kelvin. This matters because our delta S unit has Kelvin in it. So if they give you a temperature in Celsius, don't make the mistake of putting that straight into the formula. What's the difference? We'll get to that later. Good question. That's coming up. So definitely make sure that you put your temperature into Kelvin before you use this equation, because otherwise you'll get the wrong number. So at a constant temperature and pressure, a process can be considered spontaneous only if delta G is negative. Like I said, you can't use it only based on the delta H or the delta S. Those alone cannot tell you whether a process is spontaneous. That can only be determined if delta G is negative. You want delta G to be negative in order for the process to be spontaneous. So as we see, I'm sorry, I think these signs are written backwards right here. If the delta G, yeah, it's a typo. I apologize, guys. If the delta G is greater than 0, that is not spontaneous forwards. It is non-spontaneous. But like I said up here, delta G is negative means that the process is spontaneous. So you have delta G less than 0, it's spontaneous forwards. So it will happen. You want delta G to be negative in order for your reaction to occur forwards. And then you can also have delta G being equal to 0, which is at equilibrium, which we'll talk about a little bit later. You can use to figure out how much, like the temperature that you need for a state change. So this formula, or this chart, I mean, all this information is really, really useful. I highly recommend that you take a look at this and make sure you understand the trends of this chart, and if not memorize it, be able to predict it yourself, because understanding how manipulating these different signs and the magnitude of each of these components of our equation up here that we've been talking about, that is a pretty good indicator of how well you understand the concept and how well you'll be able to predict whether something will be spontaneous or non-spontaneous based on only the signs and not numbers. If delta G is greater than 0 and non-spontaneous in forward, that means it's spontaneous in reverse, right? Correct. Every time you have a spontaneous reaction, that means the reverse reaction will be non-spontaneous. And then, like this question just said, if it's delta G is greater than 0 and it's non-spontaneous, that means the reverse reaction will be spontaneous because the delta G would be negative. So back to this chart, we talked about, so just as a reminder if you forgot, delta H, negative means exothermic, and exothermic is a good thing, right? We're releasing heat. So ideally we want delta H to be negative. And so these negative ones are things we want, but let's say it's positive. And then our delta S is negative, which is also not what we want, because remember we want our delta S, our entropy, to always be increasing. Well, if we have this is positive and this is negative, there is no possible temperature where this can be spontaneous. It will always result in a positive delta G, because this is our formula up here. If this is positive and this is negative, remember negative times a negative, this component will be positive too. So if this is positive and positive, delta G will always be positive, which means there is no temperature where these signs will ever have a spontaneous reaction. And on the flip side, these signs will always be spontaneous because negative delta H is exothermic, positive delta S is increasing entropy. Those are both what we want. So if we have this negative and this positive, which is a negative in front of this, that'll be negative and negative. So there's no way for delta G to ever be positive, which means it'll always be spontaneous. Now these two columns, or these two rows, I mean, are where it gets a little bit tricky because you have conflicting signs here. When they're both the same, it depends on the temperature to be able to tell whether it's going to be spontaneous. So our negative delta H is our favorable part. We want it to be exothermic, but we're decreasing entropy of the system. And so our minus T delta S component, since it's negative, we had a negative delta S, this overall is going to be positive. And that's not really very good because we want our delta G to be negative. So even though we have a positive delta H, we want to make sure that we, if you look over here, we want to minimize the temperature in order for this to overall be negative. And so it says at low temp, it's spontaneous, but it's at high temp, it's non-spontaneous. And then the reverse is true for this, where we both have positive. We're glad that the entropy is increasing, but on our delta H, this is endothermic, and that's not what we want. And so this component up here is the part that's good about this, because this is going to be negative times a positive, so this is going to be our negative component that's going to help our delta G be negative. The delta H is what we don't want. And so if we want to maximize the influence of this component, we want a high temperature. So that's what's going to make this spontaneous. The key to these two, remembering which one, is thinking about, do you want to minimize or maximize the contribution of your delta S? So if your delta S is what you want it to be, if it's positive, then make a high temperature, because that is what's going to get your delta G negative, because it's multiplied times your temperature. So if you want to maximize your favorable delta S sign, put a high temperature on there and that'll make it spontaneous. But then if your delta H is the good one, if that's the one that's negative, but then your delta S is negative and you don't like that because that means your entropy is decreasing, then you want to minimize this component because that will cause it to be non-spontaneous. So to minimize this component, you want to make sure your temperature is as low as possible to minimize the effect of the delta S on the overall number. So that's why we say at a low temp, it's spontaneous when we have a negative here and a negative here. So I know I've taken a long time on this slide. I hope I can express to you how important I feel like it is for you to understand how this whole chart works. So moving on, determining temperature required for spontaneity. So I think that's been talked about a little bit in the chat. Since spontaneity reverses when delta G switches from positive to negative or vice versa, if you set your delta G equal to 0, that can tell you the temperature required for spontaneity. And so if we had it negative and we're like, well, how hot can I get it before it starts not working on its own? We can set it to 0, and then we can put in different temperatures and have our delta H and delta S values that come from the chart, and we can figure out what that temperature is. And so if you kind of put all these on the one side and isolate T, you can say that T is equal to delta H over delta S, and that will tell you what your temperature is that's required for spontaneity. In addition, this equilibrium where delta G equals 0, that can be used for phase changes. And so if you find the temperature, if you want to find the temperature in Kelvin for which equilibrium condition occurs, this represents the temperature required for spontaneity or a phase change. Okay, and then standard free energy changes. This delta G, the little 0 up here, that's called naught, so delta G naught, that's called the standard free energy change. The delta G reaction is when it occurs under standard state conditions. So it's like you'd have your delta G, but then it's kind of like how we talked about with the standard entropy. You put the little naught up there. These are standard conditions. And so those conditions are standard states when your reactants and products are at 1 molar or 1 atm of pressure. And so when you're at these components or these states, it's basically like STP. So you can call this standard. This is the standard free energy change. That little naught always means standard. When we had it on the standard entropy, you saw it on there too. So your standard free energy can be calculated from a table of standard values like enthalpy and entropy. And then this also, this changes with temperature. And you know that because we've been talking about this whole time, like this formula down here, don't worry about these numbers yet, but we have T in the equation for calculating delta G. And so this definitely is dependent on the temperature. But to our benefit, delta H and delta S actually are pretty insensitive to changes in temperature. And so the values that you see in the chart are going to be pretty constant over a large range of temperature values. So basically, you can use your delta H, your standard delta H and your standard delta S at 298 Kelvin, which is 25 degrees Celsius room temperature, your most basic temperature, basically. You can use those to find delta G standard at any temperature. So your standard delta G, T is just any temperature you desire, whatever the problem calls for. You can just use these standard ones from the chart for the delta H and the delta S, and you don't have to worry about those changing based on the temperature. And then there are a couple more slides of this. I'm going to let Kevin take over, so I'll give it over to Kevin.
All right, thank you, Grace. Let me see if I can pull up my pointer here. All right, so the next part is basically going to be that one section in the separate chapter. I believe it was like 16.4 for you guys. So it talks about chemical equilibrium and free energy. So K, the value of K, like the equilibrium constant, can give you the same type of information on spontaneity as delta H does. So reactions that have like a really, really large K value, which is greater than 1, you typically have a negative delta G. So both of them are going to form products and will be a spontaneous reaction. On the opposite end, reactions that are much less than 1, they're going to have a positive delta G, so it can be expected to be not spontaneous. And so also when K is 1 and delta G is 0, then neither of the reactants nor the products are formed. So this is kind of like the relationship between K and delta G. So it'll be important because you can create this formula. I won't go into details about how it's derived, but this is a good one to memorize. So delta G prime, or yeah, delta G standard is equal to negative R times T times ln of K. So R is going to be our gas constant, so 8.314 joules per mole per Kelvin. And if you recall how a log graph looks like, you can see that the larger your K value gets, the more negative the delta G does. So ln is just natural log. And you can see over here on this graph, you can see again how K and delta G are related. So as we increase our K value, so K should not be negative. It should only be between 0 and, I guess, like technically infinity. You can have like really, really big Ks, but you cannot have a negative K. So as we increase our value of K, our delta G goes from positive to negative. Okay, leave like portion of it. It should say when conditions are not standard. I'm not sure the formatting didn't transfer over correctly. So all right. So we talked about delta G here. So kind of delta G will give you like the magnitude of the K value and the kind of the position in your equilibrium, whether the reaction is more product favored or reactant favored, basically. And it'll be at a specific temperature, so that's what the T is for. So the temperature, I don't think I mentioned in the previous slide, but it'll be in terms of Kelvin. So you want to have temperature in Kelvin. And then on the other hand, if you have a set of conditions that are not standard, then you can use delta G. So just no degree sign right there. So that tells you the spontaneity of a process as it goes over the course of a reaction, and it'll be 0 at equilibrium. So delta G naught is basically more used to find K, but you can use it to find spontaneity at like standard conditions. So when you're looking at delta G, just regular delta G, these are more at like not standard conditions. So at a different set of conditions. All right. So now we're going to go over in terms of breakout rooms. So we'll be dividing you guys up real quick. I believe I got a different question earlier. So it says, are they inversely proportional? Yeah, so basically as delta G becomes more negative, then you're going to look at a K value that is more positive. All right, guys, go ahead and start doing the practice problems. Oh, okay, I think everyone just joined now. Hey guys, we're going to go over the part 2 practice problem now. So this one's asking us for the pH of a 150 milliliters, 0.2 milliliter NaOH, so that's a strong base. 80 milliliters of 0.15 millarity HBr. If you guys remember, that is going to be a strong acid. So what we have here is a strong titration. So let's write that at the top. So strong. So knowing strong, that means we want to first figure out the moles of acid and the moles of base that we have. So let's set our moles of base. 0.150 liters, right? Times 0.20 molarity. What do we get? Can you guys hear me well? All right, awesome, thank you. 0.03 moles of the base. And then again, let's do the other side for the acid. 0.080 liters times 0.15 molarity. All right, thank you. So 0.012 moles of HCl. And what is that difference right here? So I think it should be 0.018. Thank you, Megan. We have this many moles of NaOH left over. All right, so let's go ahead and figure out our concentration, right? I'm going to write OH minus. So what is our total volume now? Okay, good. 230 milliliters. So I'm going to put 2.230 liters. So I got 0.078. Let's go further. 3 sig figs molarity, OH minus. All right, so let's go ahead and plug that into negative log. And what do we get? All right, and so what is that our value of? Awesome, pOH, exactly. So we're looking for pH. We subtract that from 14. We should get 12.89. All right, so nice, strong titration. Anyone have any problems with this one? If not, we can go ahead and move ahead. So number 2 asks us to determine the sign for delta H. What's the process of NaOH was the limiting? Oh, okay. So if NaOH was limiting, so we ran out NaOH left, then we would just have HBr. And so same scenario, so we just want to figure out how many moles of HBr we have. That's our moles of H plus, right? And then you want to divide that by the total volume, which again was going to be whatever the total volume is in that scenario. In this case, it would be, right, yeah, it would give you H3O plus. And then divide that by the, I said volume, get your concentration, do the negative log, and you'll get your pH. Okay, so for determining the sign of delta S, so let's go through each scenario. So liquid nitrogen evaporating, would this be a positive or negative delta S? Right, so it would be positive delta S because we're forming more disorder. When you go from a liquid, evaporation means you become a gas. You're moving around a lot more, you have more energy in the, I guess, the molecules. And so that would be positive, more disorder. All right, so how about 2 clear liquids are heated and a yellow precipitate forms? Yes, negative. All right, so we're going to have a negative delta S because as we originally had 2 liquids and then we form a solid out of that. So a precipitate, a solid, when that forms, that's going to be more order, and that makes the system have negative delta S because more order. Having a solid is worse for disorder. Okay, and so part 3, liquid water is heated. All right, positive, awesome, thank you. Yeah, so whenever you're adding in more heat, you're technically adding in energy, you're adding in thermal energy in this case, and that'll increase the temperature and you're having more particles move around much more, bumping into each other and everything, so more disorder. Okay, what about the fourth part? All right, thank you. So this is going to be more disorder because we're looking over here. We have two molecules. And we have 1, 2, 3, 4. So 4 molecules over here. So 2 to 4 molecules. We have more things moving around. We have more disorder. So delta H is positive. And what about the surface of a lake freezing? Awesome, right. So like I said earlier, forming a solid, you're going to be creating more order. The molecules will get into, I guess, arrangements where they don't move around as much. So forming a solid, like freezing, frozen water, so that'll be more order, so negative delta H, delta S. Okay, so the entropy of a system, entropy change for a system is known to be negative 187.5, and the enthalpy change for a system is going to be negative 35.8. That's kilojoules at 25 Celsius. What is the reaction spontaneous? I know I kind of went over quickly for number 2, but let me know if I ever go too quick and I can slow down and re-explain any portion. But all right, so we have entropy. So this is our delta S. And this is our enthalpy. So this is going to be our delta H. So spontaneity is what we're looking for. So let's write out the equation. So delta G is going to be delta H plus T delta S. All right. So let's go ahead and see what we can plug in here. So let's plug in negative 35.8. So we have kilojoules per mole. Oh, I'm so sorry. You're right. It's minus T delta S. Thank you for the correction there. All right, and then T is going to be 298 Kelvin. And then delta S. So we had it in terms of joules, but to keep everything consistent, let's go ahead and convert this to kilojoules. So negative 0.1875. It's a 5. Kilojoules per Kelvin moles. Right, and so when you plug it all in, I believe someone already gave me the answer. You should get 20.1 kilojoules per mole. And so would that make the reaction spontaneous? Right, it'll be non-spontaneous because we have a positive delta G. Awesome, so this would be one to practice with just using that equation. All right, so let's look at number 4. So let's predict the direction in which delta G for the reaction changes with an increase in temperature. Oh, okay, so going back real quick. Why was it 0.1875? So if we look over here, let me change a different color so it doesn't blend in with the blue. We have here joules per Kelvin per mole, and we have for enthalpy is kilojoules. And do you remember the units for delta G? This is going to be kilojoules per mole. So to make everything consistent, let's go ahead and convert this guy to be kilojoules. All right. Cool. All right. So I'm looking at number 4. Typically, yes. Yes. They're going to ask you for kilojoules. So it's just easier to convert one of them, and it's easier to convert the delta S to kilojoules. Predict the direction in which delta G for the reaction changes with an increase in temperature. All right, so let's set this guy up. So we should have a delta G not equals delta H minus T delta S. Okay, so let's just choose a random temperature, right? Let's put out here, so negative 92.35. So that's kilojoules per mole of the reaction. And then we're going to have here negative, let's go ahead and convert it, 1.1983 kilojoules per mole Kelvin. And let's just choose a number. Let's say standard temperature is like 298 Kelvin. Can anyone tell me how much this would be? What the value would be? All right, thank you. Negative 33.29. All right, so we have a set point. How about we change the temperature to, let's make it be 500 Kelvin this time. We're just increasing it, so it doesn't matter how much exactly. Let's see what we would get. Okay, we have 6.77 kilojoules per mole. So this is going to be spontaneous originally, but now it's non-spontaneous. So this is one of the ones where as you increase temperature, you're becoming non-spontaneous. All right. Let's go ahead and move on. Okay, so for a reaction in which delta H is equal to let me 1 second. Pen is acting weird. Okay, now it's ready. So what's the direction? So it proceeds, yeah. In the previous one, depending on the temperature, so at high temperatures, it's going to be non-spontaneous, so it'll proceed to the left. But at low temperatures, it's going to be spontaneous, so it'll proceed to the right. All right, so for a reaction, delta H, we have a value, delta S, we have this value. You want to find the temperature in Celsius above which the reaction is spontaneous. So that means we're going to go convert things around. Equals delta H minus T delta S. All right, cool. So we know at equilibrium, or when delta G equals 0, we have that one point right between in which they are spontaneous. It's T delta S. All right, so let's go ahead and can isolate for T. So moving point out the pointer, this guy to the other side, and then dividing by delta S, I have T equals delta H divided by delta S. All right, so let's fill in our numbers. 125 all over, it should be 0.325. And what did you guys get here? Should be 384.6. 3.4, 34.6. I'm not sure about the 100. Oh, in terms of Celsius? Oh, okay. Got you. You guys jumped right ahead. Thank you. So this is in terms of Kelvin, and then converting to Celsius, so minus 273.15. We can say it is 111.5 degrees Celsius. All right. So that was number 5. Again, if any of you guys have any questions, feel free to stop me at any time. I can go back. Otherwise, we'll move on. Okay, so indicate whether the following statements are true or false. So a spontaneous process is fast. Is that true? Okay, right. So it's false. So one example of a false part is what is that, like rust? So rusting takes typically a long time. Okay, and then under any given set of circumstances, a process that is spontaneous in one direction is non-spontaneous in the opposite direction. What about that one? Yeah, so it's going to be true. So if you're spontaneous and you move to the right, then you're going to be non-spontaneous to the left. All right, so moving on to the third part. How about spontaneous processes are exothermic and increase order to the system? Right, so typically spontaneous processes are, for the most part, typically are exothermic. However, they're also decrease order in the system. So you want to have a decrease of order, typically, for spontaneous processes. So let's move on to the next one. Water evaporating into steam at 25 degrees Celsius in one atmosphere is a spontaneous process because the water gets hotter and turns into a gas. All right, so I'm getting two conflicting answers here. So, right, the answer key says it should be false. It's a spontaneous process. The water gets hotter and turns into a gas. Well, the boiling point. Oh, all right. Let me see here. That went a little bit over my head. I'm sorry. I ran over it, and I was just looking at one atmosphere. It's hotter than steam. But yeah, the boiling point here is not true because it should be 100 degrees Celsius. So if you're at one atmosphere, you should be at 100 degrees Celsius in order to get water turning into a gas. All right, so for number 8, dissolving sugar, water, and salts are both processes which increase entropy. Right, yes, that's true. So as we're adding in more solutes, we're increasing the disorder because they're dissolved. Right, so for the solutes, dissolving into the solution, So there's going to be some, you're going to break apart. So like you'll have like chunks, like think of like a sugar cube. Whenever you're at a solid, you have like kind of chunks of molecules and they're breaking apart. And however, for the solvent, you're going to form new bonds basically between the solute and the solvent. So there's going to be this little order that is formed, but it's mostly a lot of disorder because you're adding in a ton of new things. We want to say that the solution has greater entropy because we are dissociating and we're having more molecules interacting with each other. So let's see your statement, Toshi. There's no sugar water. Is it correct to say, but when compared to sugar? I'm not sure I understand like the question. So they both increase the entropy of the solution because the solution originally only had water interacting with itself, and now you're adding in extra sugar and salt. So you're creating more disorder. So there's more molecules moving around, and they're interacting with each other. So that's what kind of creates that disorder.
Can I just ask, can I talk because it's easier?
Oh yeah, go ahead.
So my question is, like salt, it dissociates into Na plus and Cl minus, but
Yes.
sugar will just stay the C6H12O6. It will just dissolve into water. And so if you're comparing the two solutions, does the solution with salt have a greater increase in entropy than the solution with sugar because it splits into two, a cation and an anion?
I want to say that's a good statement, but on the other hand, there's also like the more mass a molecule typically has, the more entropy it also brings into a system. So like sugar is only one molecule versus two molecules for sodium and chloride, but sugar is like a larger, more complex molecule. It has like two carbons and it has like three hydrogens. I forget the exact formula for sugar, but it's going to be like a heavier molecule typically. So for that one, I would have to double check with the professor. I want to say yes initially, but then thinking about like the mass that sugar has might also play a factor in determining how much entropy exactly is brought in. Now, good question. Sorry, I can't give you like an exact answer. Okay. So on number 7 is asking, under what conditions are the following reactions spontaneous? Are they all none, high temperature, or low temperature? So let's take a look at the first one here. We have a negative delta H and we have a negative delta S. So will it be spontaneous at what conditions, or will it not be spontaneous ever? Right, so at low temperatures, these guys will be spontaneous. Awesome. All right, so for 7b, we have a positive delta H and a negative delta S. Awesome, yes, so it will never be spontaneous. 7b is always non-spontaneous. What about C? Right, so we have a negative delta H and a positive delta S. So exothermic and increasing disorder. So we're always going to be spontaneous. Awesome. Right, so remember that table that Grace was talking about earlier is pretty important to memorize. It looks like you guys have it in the bag so far. Awesome. So moving on to number 8. Okay, so let's kind of look see here. So the KSP for strontium chromate is 3.5 times 10 to the negative 5, and the KSP for barium chromate is 1.2 times 10 to the negative 10. And then potassium chromate is, so this is the scenario, potassium chromate slowly added into a solution of 0.30 molarity of barium plus and then strontium plus ions. So we're adding in potassium chromate, so it'll be K2CrO4. All right, so what concentration of potassium chromate is needed to precipitate the max amount of either compound without precipitating the other? So we're looking to precipitate one of the compounds as much as we can without the other. So which one would precipitate first? Right, so our barium chromate, because we have a much smaller value. So let's go ahead and write that out. KSP for barium chromate is going to be Ba2 plus times chromate, CrO4, 2 minus. And set that equal to the KSP, so 1.2 times 10 to the negative 10. But we know that we already have 0.30 molarity for the Ba2 plus. And so what we're looking for is what is our X value here. So can anyone tell me what that is? Okay, so it's going to be 4 times 10 to the negative 10. So that's the minimum amount that we need to start precipitating barium chromate. But what is the max amount that we can precipitate without precipitating the other? So that means we need to check out the KSP for strontium and make sure that we're not going over what strontium is doing. All right. Oh, okay. I don't have my calculator with me to do like these scientific notation, so I'll go along with what you guys are saying. But for the 4.4 times 10 to the negative 10, right? So when we set up this, let me pull out my pointer. When we set up this equation, we have 0.30 for our concentration of barium. That's what I said is in solution. And then we don't know what is the concentration that we need for chromate in order to get this KSP value. So that's why we were solving for this X value right here. So we divide that by 0.3 and we can get this value right here. So this is the minimum amount of chromate that is needed in order, so in terms of molarity, that is needed to start precipitating barium chromate. But now we're taking a look at strontium chromate. So what's the max amount that we can precipitate without precipitating the other? So we don't want to precipitate strontium chromate, but let's see how much we would need in order to do that. So again, this is very similar. So it'll be 0.03 for that value, and I'll call this a Y value. Just not get them mixed up. Okay, so do you guys tell me what Y is? Awesome, thank you. So 1.2 times 10 to the negative 4 molarity. So that means we can have up to this much before we start precipitating strontium chromate. So anywhere basically between this value of chromate and this concentration of chromate, we will be precipitating barium chromate, but not precipitating strontium chromate. All right, so moving on. I guess this, I understand this is kind of confusing. So just let me know if there's any part you want me to clarify. All right, moving on. Okay, so this one's kind of long. So for number 9, let's consider the titration of 100 milliliters of the 0.200 CH3 NH2 by 0.1 molarity HCl. So we're going to look before any HCl is added. So before any HCl is added, what do we want to do? What is our game plan? Moles. So before any HCl is added, we're at our initial point. So we want to do an ice table. So let's look at our reaction here going on. So we have CH3 NH2, and it's going to react with the water that it's currently in. And so you'll have CH3 NH3 plus and OH minus. So ice table, we have 0.2 molarity. We can ignore the water. 0, 0, plus x minus x, x, 0.200 minus x. All right, and so let's set up an expression. So we have Kb equals 4.4 times 10 to the negative 4 equals x squared all over 0.200 minus x. Okay. And looking at this guy here, so far let me pull my pointer. This value and this value is they're different enough by a factor of about 1,000, so we can do excuse me, a small x approximation. So let's go ahead and ignore that x, and then we can get our x value. Yeah, so we'll be doing all 6 of these. So this will be like kind of a long one, but we only have like 12 questions in total. But this one will be like a multi-step. So if you guys got the value of x, it should be 9.38 times 10 to the negative 3 molarity. And so what does that equal? It's going to be equal to our OH minus concentration. Awesome, thank you. And then from there, we can just plug it into our pOH value, so negative log of that number. And we should get 2.03. And then from there, we get our pH. So 14 minus 2.03, I got 11.97. All right, so go ahead and clear the board. Does anyone have any questions on how to do part A? When do we use moles versus molarity for these problems? So whenever you're doing ice tables, I'd say you want to stick with using molarity. So at our initial point and then at our equivalence point, you want to stick with molarity, but in between you're in the buffer region. So that's when you don't really need to use the ice table because you're using the Henderson-Hasselbalch equation. And in the Henderson-Hasselbalch equation, that ratio of acid to base, or sorry, base to acid, conjugate base to acid, you can just use moles there. No problem, Mackenzie. All right, so after 20 milliliters of HCl is added, so let's go ahead and find how many moles of HCl that is. So first off, let's find out how many moles of base we have up here. So that's going to be 0.100 times 0.200. So it should be 0.02 moles of base. I'm not going to write the whole thing out. And then, so that's for moles of acid, right? So we have 0.002 liters of acid times 0.100 molarity of the acid. Gets you what? 0.002 moles of the acid, HCl. All right, so when we combine these together, what is our limiting? Limiting is going to be our acid. So limiting is our acid, therefore we're going to go ahead and subtract. So we're going to have 0.018 moles of our base left. And then we're going to have created 0.002 moles of the conjugate base. So that's going to be, I want to say C base created. Okay, so when we do the Henderson-Hasselbalch equation, because we're doing weak base, strong acid, here's an alternate version of the Henderson-Hasselbalch for POH. So I'm going to show you two ways to do these kind of questions. All right, so we have POH. So that means we're going to do P KB plus log of the base over, sorry, under the conjugate acid. Okay, so that's negative log of 4.4 e to the negative 4 plus log of, should be 0.002 over 0.018. And tell me what you guys get for these. Or for total, like once you get the value and add them together. All right, y'all got 2.440. Awesome. So again, that's our pH. So that means we're not done. We're looking for, sorry, that was POH. We're looking for pH. So that makes our pH equal to 11.60. All right, that one was kind of long. But I guess I would say the main takeaway is understanding you're in the buffer region of Henderson-Hasselbalch. You have your weak base and you have your conjugate. Sorry, I wrote conjugate base. I meant to write conjugate acid. Conjugate acid was created. Right. And so here's your Henderson-Hasselbalch version of the POH. In case you guys haven't seen that. All right, so I'll move on to the next one. Oh, sorry. We're technically still on this one. All right, so for number 9, C, let's say 65 milliliters is added. So originally we said that we had these guys is 0.02 moles of this base. Now we're adding in 65 milliliters, right? So 0.065 liters times 0.100 molarity equals what? 0.0065 moles of HCl. All right, so with that many moles of HCl, we can go ahead and compare them. So it looks like we have more moles of base than we do moles of, I think my pointer froze, more moles of HCl. So that means we'll run out of the strong acid first. And let's see here, how much do we got? So we'll have 0.0135 moles of the base created left over. And then we'll have 0.0065 moles of the conjugate acid created. All right, so again, we have base and conjugate acid, so we're going to create the Henderson-Hasselbalch equation. We're in the buffer region. All right, so we can use the regular pH one. This will save us like a step from subtracting. But I just wanted to show you guys how to do it this way. pKa plus log of the conjugate acid, conjugate base, basically your base over the acid. All right, so what's a little tricky for this one is that we don't have our Ka value to get the pKa, so we'd have to solve for pK, or solve for Ka. So remember, Ka equals Kw over Kb. So I'm just plugging in this value, and then Kw is 1 times 10 to the negative 14. And what I got was 2.27 times 10 to the negative 11. And then when I get the pKa, well, I just write it down here. Yes, we can do that. I just want to show you guys this other step, so you guys can make your own determination on which one you would prefer to do. Whether just to use the other equation or just keep everything, just to memorize like one equation. To 7 e to the negative 11 plus log of the base or the acid. Just like that. And can you guys tell me what you guys ended up getting? If you did it the other way, you should get the same answer as well. So I ended up getting 10.96. For the pH. All right. Yeah, so whatever, if you thought this method was more tedious than the other method, then go ahead and do the other one. Or if you like this one better than the other one, then you'll have this one in mind that you understand how to plug in the right numbers. All right, so I'll go ahead and move on to the next one. Clear the board. Okay, so at the equivalence point, so what is our pH? Okay, so So at half equivalence points, that's pretty close, Tochi. But half equivalence point is where pH equals pKa. So we're at equivalence point, which is different. All right, so we originally had, what was it, 0.02 moles of our base. So we're at equivalence point, so all of our base is converted into conjugate acid. So what is the conjugate acid? CH3 NH3 plus, right? So let's go ahead and say that it reacts with water, because that's what happens at the equivalence point. It's going to try to reform some of that base. And then we're going to also have H3O plus. All right, so we can set up an ice table. So these guys are both at the time for the time being. All right, so what you're looking for really is what is the initial concentration of this conjugate acid. So we know, since we had, let me get my pointer out, we had this much moles of base, we're going to get this moles of conjugate acid. So all of our base converted into conjugate acid. So now we're going to go ahead and figure out our concentration, right? 0.02 moles. But what is our volume? We don't know what our volume is, right? So we know we had 100 milliliters at least. So we need to figure out how much volume of acid we added. So we need, basically we need 0.02 moles of acid to be added in to use up all of our base. Acid. Okay. All right, so now we're going to say, let's see, do you remember, is it molarity equals moles over liters? So we can say liters equals moles over molarity. So we're going to put 0.02 all over 0.100. So that will give us R 0.200 liters of HCl is added. So that's 200 milliliters, and then we have our 100 milliliters here. So we have 300 milliliters in total. And so now we can get our concentration of the conjugate acid. So that'll be 0.0667 molarity. Oh, yeah, 0.667. Awesome. So we'll be subtracting, adding, x 0.0667 minus x. Cool. So now we have to set this equal to x squared over 0.0667. What do we set it equal to? So we use Kb whenever we're having a reaction that produces, that is reacting with, sorry, we use Kb whenever we have a base that is reacting with like water or something. However, if you notice this guy, our reaction here, we produce H3O plus, right? So that means our guy right here is an acid. So therefore, we have to use Ka. So Ka is for acids, Kb is for bases. So we're going to use Ka, which is Kw over Kb. And so that's going to be equal to, I'm just going to write it out for you, but you guys know how to solve it. It's Kw divided by the Kb we're given. Oh, sorry, this should be a 3. Then e to the negative 11. All right, so another thing we can do, we can compare, look at the value of that Kb and the value of our molarity here, and say, oh, I can do the small x approximation. They're significantly different enough. Therefore, our x value is equal to, I got 1.35 times 10 to the negative 6. I'm not sure what you mean by debow. Oh, Henderson Hasselbalch? No, because we're out of the buffer region. So I can go back to the scenarios. So before anything is added in, we have an initial point. We want to use our ice tape. And then as we go through, we're going to be adding more and more base. We're going to be, sorry, more and more acid. We're going through our buffer region. So this is when we use Henderson Hasselbalch, only in our buffer region. And once we get out of our buffer region, once we pass, or once we're at the equivalent point and beyond, we're beyond the buffer region, so we cannot use the Henderson-Hasselbalch equation anymore. The Henderson-Hasselbalch equation is only for the buffer region. Okay, and so that's our value of concentration of H0 plus, and our pH is going to be the negative log of that number, and that's going to be 5.87. Nice. All right, any questions on the equivalence point portion? All right, and if there's no questions, we can move on. All right, so second to last part 300 milliliters of HCl. Okay, right here again, we had 0.02 moles of base, like I said in the previous ones. And so now 300 milliliters is added, so we have 0.300 liters times 0.100 molarity is equal to 0.03 moles of HCl as we're adding in. So it looks like this time our limiting reagent is going to be the base. So we're going to have excess of the acid. So we're going to have 0 base. Oh, it should be an M. But we'll have 0.01 moles of HCl. Oh, HCl left. So from there, we can just say basically pH is equal to negative log of the H plus concentration, so it's going to be 0.01 divided by, looks like we added 100 and then 300 milliliters, so we'll have a total of 400 milliliters. And then I got 1.60 for that. Once you break past the equivalence point, then basically you're just doing excess, so you can just do pH equals negative log. All right, cool. So I'll go ahead and clear the board. So at what volume of HCl does the pH equals 10.643? So do you guys remember the pH at the equivalence point? So pH at the equivalence point I said earlier, we saw that earlier was 5.87. And so if you look at, let's say like a general graph. So our general graph, that's a bad one. A general graph looks kind of like this. So as we're adding our acid, we're slowly lowering down our pH until we reach something like that. So if our pH equivalence point is going to be like right here, like 5.8 something, 5.87, and we're saying our pH is 10.64, then we know at our equivalence, or we're going to be above that, so that means we're in the buffer region area. So if we're in the buffer region, that means we can use the HH equation. That should be an H. Okay. Awesome. So we know if we can do the HH equation. Let's go ahead and figure that out. So pH equals pKa plus log, let's get the A minus over HA. So basically the base over the acid. Okay, so pH 10.643. What is pKa? Right, so we have Ka equals Kw divided by Kb. So we said earlier that was 2.273, I said. Let me double check my work here. All right, 27 and negative 11. What is our pKa? .643. So 10.643, right? Plus log of A minus over HA. So we notice that these two guys are the same, you know, the color. So we have 0 equals log of A minus over HA. So we know that 1 is equal to A minus over HA. So the moles of A minus and HA are going to be the same. So we know we're at the half equivalence point. One half equivalence point. So do you remember from 9D how much acid we used? If you guys remember, we used 200 milliliters of HCl at the equivalence point. So that means we're going to use 100 milliliters of HCl at half equivalence point. All right, so the answer would be 100 milliliters. Okay, so this one was kind of tricky. We had to work backwards. I think the main part to start it was to realize where you are in the titration curve. So we know our pH at equivalence point was 5.87, and we're told our pH is currently at 10.643. So that means we're before the equivalence point, so we're within the buffer region. Therefore, that prompts us to use the Henderson-Hasselbalch equation right here. We don't know our pKa, so I had to solve for pKa using Ka equals Kb, Kw divided by Kb, and then getting your Ka value, getting your pKa value. Then you subtract those, and we notice that it was equal to 0. And so log of what is equal to 0? Log of 1. 1 is equal to this ratio. And so we know if these two guys divided by each other is equal to 1, we know that they're the same They have the same molar values, same number of moles. That means we're at the half equivalence point. All right, and because we solved for the equivalence point earlier, we know it took 200 milliliters of HCl. Half equivalence point basically just means half of the volume of acid as well. So we have 100 milliliters. Okay, any questions on this one? All right, if there's no questions, I'll move on to the next one. What was the answer for 4 again? So 1, 2, 3, 4. Oh, okay, so for, I think that would be 9D. All right, so for 9D, we had the pH is equal to 5.87. All right, of course, no problem. All right, so moving on to 10. So we have here 2 milliliters of 0.1 molarity NaF, and to 128 milliliters of 2 times 10 to the negative 5 molarity of calcium nitrate in well precipitate form. So we're given our KSP value. So we're basically asked to find a QSP value. So what is our QSP? Well, actually, let's go ahead and write out what reaction is going on here. So we have NaF plus CaNO3. So if you remember NaF, it's going to be aqueous because sodium is spectator ion. If you remember calcium nitrate, NO3 is going to be spectator ion, so this is also aqueous. And so we're forming Na3. So that'll also be aqueous. They both spectator ions. And then calcium fluoride. So this one is the solid. So it should precipitate. So this is our balanced equation. All right, so back to doing the QSP. So QSP, well, actually, let's go ahead and continue on with this one portion real quick. So this is the reaction we're really concerning ourselves with here. It's going to make calcium 2 plus, and then 2F minus. All right, so now we can go back and form our QSP. So we have Ca 2 plus, and then we have F minus squared. So set that equal, or actually I wouldn't set that equal to what? Okay. Is it 2F squared? Let me double check my notes really quick. No, I don't believe so. So that should be. So we need to figure out basically the concentrations, because now we're changing the volume, because we have two different volumes added together. We went from 128 total volume to now 130 milliliters of total volume. So we need to find our moles of F minus, basically. Well, how many moles of F minus do we have? It's going to be equal to, I'm going to say our volume, so 0.002 liters times our molarity, 0.1, equals 0.002 moles. And then our moles of calcium nitrate. So basically looking for a molar calcium. So that'll be 0.128 liters times 0.1234 molarity. It's a really small number. So we should get 2.56, sorry, e to the negative 6 moles of calcium, Ca2 plus. All right. So now, looking back at our QSP, we have to have this in terms of concentration. Negative 6 all over 0.30. Remember we said we have a total volume of 130 milliliters. And over here, 0. Is that right? Yes. Divided by 0.130. Yes. So what I'm doing here is trying to account for the change in volume. We go ahead and get the pointer out. So right here, I had to do moles. So I had to find the moles of F minus that we had and the moles of Ca plus, Ca2 plus we had. And then divide it by their new volume, which is 130 milliliters, in order to get their new concentrations, and then you multiply everything out here together. All right, and so that'll give us 4.7 times 10 to the negative 11. So what does that mean a precipitate will form? Yes. Awesome, yeah. So basically, once you have your QSP, we want to compare it with our KSP value. So we see they both have times 10 to the negative 11. Then we compare our coefficients, or I forget what this number is called in front of the or in front of the times 10. But we compare that number. So 4.7 is greater than 3.45. QSP is bigger than KSP. We know a precipitate will form. We have too many products. Too many products on this side. All right, any questions on number 10? Okay, so I'll move on to the next one, number 11. So estimate the solubility of barium sulfate in a 0.02 molarity. Precipitate form if Q was greater. Yes, so on the previous question, number 10, we said our QSP was larger than our KSP. So a precipitate did form, yes. Okay. All right, so estimate the solubility, barium sulfate in 0.2 molarity, sodium sulfate solution. And the solubility constant, KSP, is 1.1 times 10 to the negative 11. So let's look at our reactions going on. So we had barium sulfate. So that's going to break apart into barium 2 plus, and then sulfate 2 minus. Okay. Okay. So the idea here, you could just do like an ice table. So we ignore this guy because it's a solid, and we start off with 0 in this barium column, but we do have 0.020 molarity of sulfate because of that sodium sulfate solution that we're in. So we're going to add x, x, 0.2 plus x. All right. So now we set up our KSP value, 0.1 e to the negative 10 is equal to Ba2 plus SO4 2 minus. We have X here, and then we have 0.020 plus X. Okay, and so now we think to ourselves, oh, can I do small x approximation? Let's compare the K value with our molarity. So our K value here is times 10 to the negative, times 10 to the negative 10. And then we have here would be like, if you just move the the decimal place over 2 times, then we're basically times 10 to the negative 2 power. So they're significantly different enough that we say, yeah, we can ignore this x. And so we're basically just saying this number times x times, or is equal to x times 0.02. So that makes our calculation a little easier for us. So I got x equals 5.5 times 10 to the negative 9. Molarity. Okay, and are we done here? Right, yes, we want to go one step more because we're told to find solubility. So what I found here was molar solubility. So to find solubility, you just got to multiply that by the molar mass. So I'll tell you guys a molar mass of barium sulfate. That's going to be 233.38 grams per mole. Let's go ahead and multiply that. 233.38. We should get 1.28 e to the negative 6 grams per liter. So that's our solubility. Okay, any questions on number 11? All right, one last problem, number 12, and then we should be done for the night. Okay, so number 12, the standard free energy of formation of for a reaction is negative 33.2 kilojoules per mole. So that's our delta G naught. Then you want to find the equilibrium constant for the following reaction at 298 Kelvin. Okay, so we're basically looking for what K is. We're told a delta G naught. 3.2 kilojoules per mole. Okay, so let's go ahead and think to ourselves, what value do we have? How do they relate? We have this equation, remember? Delta G naught equals negative RT ln of K. Oops, that's an N. Okay, so let's go ahead and find K. So K equals, how about ln of K is equal to delta G naught divided by negative RT. And then we can say K equal to e to the negative delta G naught all over RT. So if you guys remember, let me go ahead and switch to a different color. T's in kelvins. Oh, I think I have a little lag on my end. Okay. T equals negative, or sorry, not negative, 298 Kelvin. R is equal to 8.314. It's joules, I believe. And then more units, but most importantly is that we know this is in terms of joules. So that means our delta G should be in terms of joules as well to help compensate for that. So let's say this is negative 33200 joules per mole. So here, negative 33200. Okay, so our negative out here is going to cancel out our negative there. So what do you guys get? Should be 6.6 times 10 to the 5th power. So pretty big number. So that tells us that this k value is large, so that means we're going to be product favored. Okay, so this is just a really quick overview of our presentation tonight. So with that being said, I'll stay behind if anyone has any questions over the presentation or I guess over exam concepts in general. Other than that, you guys are free to go. That's all we had for you tonight. All right, thank you. I appreciate that.